Hi everyone, this is a lecture presentation for Open Vessel, our medical imaging technology company, on how to read DICOM files. So this is for new interns, new people to the company, or anyone who's interested in learning about this technology and the field of medicine and the data that goes with it. So let's get started. Okay, I will be your lecture teacher, Leslie Wubble. I'm going to tuck myself in the bottom here. If it would let me. There we go. All right, let's get started. Wrong way to do it. Swap. All right, so how to read DICOM files. So before we read DICOM files, I'm going to explain what they are, but I want to explain people who might work with them. So radiologists, how do they do their work? How does data factor into their work? So a CT scanner is going to generate a scan of someone's body or lung, or an X-ray machine might also scan somebody's, top part basically of their chest, and they might scan someone's brain. That generates image data. A radiologist interprets that data and then reports to a doctor. In general, how does data factor? Like any other discipline, they have valuable insights that they only as people can really generate. It's kind of, radiologists are specialists who can only interpret this image data and correctly define what is, a tumor, what is not a tumor on these images, because it's in between science and art at the same time in these interpretations. And they have, specialists who spend maybe 20 plus years in this field. So a reason why we're here is that there's too much data, too little time. We could have radiologists working 9 to 10 hour shifts every day with hundreds of cases per day. A workload might look something like 70 X-ray scans, 10 CT scans littered in, and then 2 MRI scans. It varies a lot day by day. And then in some cases, I've heard trauma cases having 3,500 images to 4,000 images a person has to look through. And then lung scans are somewhere around 200 to 400 images depending on the scanner. In general, higher quality scanners generate higher quality data and higher resolutions because technology is advancing so much. But the amount of image data that is being generated is getting to a point where radiologists are kind of feeling burnout, such as our gentleman here in the photo. So this is what actual workflow would look like: is that the patient comes in for a scan. It's captured through a hardware device and then is put into a DICOM format. And those images are scanned and stored on a server. This will get passed on to RADs, or like a radiological department. Sometimes they hire people who transcribe these reports. And when the radiologist or technician is viewing these documents, they're generating and assessing the report and passing that on to the physician. So before I begin talking about DICOM files, I want to explain, that was a lot of workflow and that was a lot of information. What we're starting with essentially is the data, is the raw material. This is considered upstream for us. And then downstream is really the outputs like visualization, graphs, the image itself, location information of some abnormality. We're passing this data through several programming functions that is cutting the size of the data down, looking at data that is only apparent to the disease case. So how well detection and classification of a disease happens downstream is really affected by the upstream process, especially in this pre-processing area. So for this lecture, we're only focusing on data and pre-processing. So here, our data can come in the form of DICOM files. In research, they're also known as NIfTY files, which is a form of neurological imaging files. And HL7 is a form of electronic health record. It's a way data is stored about the doctor who diagnosed the patient, the patient's name, things like that. And this data is usually moved into the pre-processing, where we're loading data into a memory or a programming object that can be manipulated, and we can extract information that matters. In our case, for this example, we're going to be extracting pixel values out of that, and we'll plot some of these values as an image or a graph. So what is DICOM? So DICOM is essentially a data structure and a networking protocol. It essentially allows hardware manufacturers to define how their binary data that is generated, let's say out of a CT scan, and when it's put in a DICOM file, other hardware in the medical center can communicate and understand what that data is saying. So it's this idea of intro operability where, whatever the data is, if it's text files, images, it can be communicated between computers without a hiccup. That stands for Digital Imaging and Communications in Medicine. What you need to look for is a DICOM file comes in extension of DCM or DICOM, and it essentially stores the image on a right here of somebody's, this is a 2D image of someone's body cavity in their lungs, and then in the middle is the aorta and heart, and this lower section is their spine. Excuse me. And essentially, this is what the DICOM data, how it's organized. You'll have a header and you'll have a data set. And the header contains a lot of binary information related to the machine, the day it was generated, its class, instance, unique ID number, ID. DICOM data can be really flexible in terms of what it contains. But what really matters in our case is the data set. This will contain information like the patient, study, the number of series related to a patient. You can have one patient and then 4 series related to that patient. And that's essentially what the series is kind of related to. What matters here is down here in image, this contains the pixel data that we want. And so each section of this data is defined in a module and then an attribute. So this will also help us with our programming code if you're familiar with Python. So the way the data is structured is in a key value pair. So a group has a unique number like 28, and it uses 28 to relate to the group name. So all these groups here, 28 relates to the image group like I showed you in the last slide. And then the data element will have a unique number. So you have an element 4, 10, 11, 30, 100 that contains their own data. So to get pixel data is in its own little data element, and you can reference that in the programming code to pull that stuff out. You don't have to use this hexadecimal thing specifically, but you'll see in the code in the next part of the lecture what I'm talking about. You can go to this link to read more about this type of information. So like I said, this is just another example of what the header will look like. At 002 is that tag group for the header information, and then data elements like little Eden just explains here the encoding of the CT machine, or if they implemented something in MATLAB, that's really what they're explaining there. There's more links at the bottom. The presentation will be linked below in the video. So when you open a DICOM file up, this is what it looks like in hexadecimal. Here is our header at the top, is relatively empty, and then DICM is defined here. This doesn't really make a lot of sense to us as humans, so here it is. Our header is defined here with preamble, prefix, and then data elements. And here, this tells us it's a DICOM file. So this data structure is really just organized binary, and this is how the structure relates in reality. Okay, so the reasons why DICOM matters is that all the X-rays, CT images, MRIs, ultrasound, PET scans are in the DICOM file format. It's what you'll mostly get as a researcher or a programmer, is this type of data. So the way a DICOM image works is that when a CT scan takes a scan of you from the neck, from the neck top to the diaphragm, each cross-sectional image that is made here is put into order going down into a stack. So one DICOM file represents one 2D image, the next DICOM file represents the next image under that. Kind of like the way cake is stacked up. So you have all these 2 images stacked up on the top of each other, it generates this 3D data. So the way that this happens in a CT scan, I think physics play a very important part here, because the wavelength of your X-ray tube hitting the patient is going to lose energy when it goes through that patient. So you're sending energy in one way and then receiving energy on the other end with these detectors. And the energy that's displaced generates voxels, or these 3D pixels, in this 2D image that we saw before here in these stacks. So again, pixel data and metadata. Each of these DICOM files that I showed you in that folder image, they're their own slice, and each DICOM file has their own metadata. And so we have to take the pixel data out of each DICOM file and put them into numpy arrays in the Python coding. Essentially, numpy arrays are used for matrix math, and they're used in deep learning models. Everything that you process into these models are going to take things into a numpy array, and that's essentially what you need. The Python package we'll be looking at is PyDICOM. It's well developed and kept up regularly, and used by several excuse me, speech impediment, kept up with several researchers in general. So they got well documented code that we use there. So now, to think about pixel data, we need to think about the voxels. On a graph, you have a Y and an X, and that's on JPEGs and PNGs. You kind of, a JPEG is really just, if you think about it, a bunch of squares in a graph, and each square containing a color value. Well, in in a 3D space, you're going to have a Z, and that's how thick that slice image is, how thick that image is. That gives you a 3D area. And inside this color defined area, there could be a tumor in this box, this 3D space, that the model or the program will be looking at. And like I said, I'm bringing this up again because this is where the pixel data is all contained in this data element. So I explained how does this factor into the data. Like I said, if we look at a JPEG of Mr. Lincoln here, I got this from a source in the PowerPoint, where essentially each of the pixels you see have a unique color value. But these color values are going to range from a grayscale factor of 0 to 250. When a human eye is kind of looking at this image, these numbers are making, a pattern that our eye can recognize essentially. Here, this is essentially an artifact in the patient. Sometimes that's a pacemaker. These are two lungs. Your lungs are different sizes. I think your left ventricle is a little bit larger, if I remember right, or the right. Don't quote me on that. That could be a little bit wrong. And then we have this body cavity of the patient. And then air is even picked up on the outside. So these values are really important for doing computer vision and evaluating the data in the image itself. So it all comes down to numbers. The darker a pixel is at 0. The lighter a pixel is, it's at 255. This pixel range can also change depending on your bit size. If I have 1 bit, you have black, white. If you have 2 bits, you have 4 different colors. But we're at like 16 to 32 bit, 64 bits types of resolution on an image currently. So that's what I mean by when scanning technology gets higher and better in this bit range, we get higher resolution images. So how do a radiologist evaluate these pixels and image? They use a quantitative value called Hounsfield units. It's just a way to represent radio density. You want to write this quote down and understand it the best you can, but Hounsfield units are proportional to the degree of X-ray attenuation and is located to each pixel to show the image that represents the density of the tissue. So let's break this down. So when we get a CT scan and we look at the CT scan and its pixel, the HU unit is simply a conversion of pixel data into a HU value. So in the next slide here, I'm kind of going to show you what I'm talking about. So we have an X-ray bulb generating 100 kilowatts. It goes through a patient, and that signal is now 80 kilowatts. That's because your tissue absorbed that energy. And when we take those two numbers and subtract them, we're left with this attenuation coefficient. And this number, this 20, is what's saved in binary. That is the signal that is detected as that difference in the computer. And then that pixel, that volume is converted in Hounsfield units. It just describes how much your tissue absorbed in the scan itself. It's fairly harmless. Obviously, you don't want to give patients higher dose of radiation, so They're always developing algorithms that can determine what is the least amount of energy that we can, hit this person with while generating an image. So in this linear attenuation coefficient here, we can see the conversion of the pixel data into Hounsfield units down here. So air is actually the value of 0 for our pixel grayscale. So 0 is black as a pixel, and now it's negative 1,000 on the Hounsfield unit. So if we go back to this calculation here, you plug in your volume or your numbers for the pixels, and then you multiply by 1,000. If we plug in 0 for water and air, we can see that we're just going to end up with negative 1,000. And then water itself ends up being 0 because the way the conversion works is that you're using the number 0 as water as a default standard to convert. And then when we do blood, the pixel values are much wider and there's gray scale, so we kind of get a 35 to 40. And this is kind of what Hounsfield looks like. You have negative 1,000 for air, and bone can be plus 1,000, and it shows up white on the image itself. So essentially what is happening here is that HUs are being transformed into a function. So we're getting a linear transformation of the original attenuation and measurement. So here you're getting, we're going to use slope. This is back from algebra, if you remember, is y equals mxb. They take the slope and the intercept and they multiply that against the grayscale pixel value as our x to calculate for our HU values on the graph. So what's happening in the code as I show you here is that out of each slice, out of each image, we are taking the rescaled intercept and the rescale slope out of the data and using that to calculate for HU values, because we're converting pixel values to HU values, because HU values help normalize the data and can tell us which pixels are going to be part of a lung tissue or going to be bone in general, mathematically speaking, and statistics and classification plays a role into this. But we'll take these easy steps here. But what we did is here we set two variables, intercept and slope, and multiplied them against the raw pixel image here as a float, and then we're generating a new value to be kept for analysis. So what happens when we convert it is that we can now tell which parts of the image are going to be gray matter, white matter, liver and bone, and lung. And the reason we want to do this is that there are many factors that go into generate a CT image. Excuse me. Where are my antacids? Having acid reflux. Excuse me. The reason why we do this is to normalize the data. A larger patient makes the data volume much larger, and the spread on a graph is going to be much wider compared to a patient who might be much smaller. The X-ray tube's energy that is being sent towards the patient varies a lot. So these are all elements that go into the process. So like the type of scanner, the size of the patient, and the voltage on an X-ray tube can all affect how well that grayscale pixel is determined. So I have a pixel scan, I have a CT scanner from GE Health that generates some CT data. I have a Siemens scanner below right here and a Philips scanner. They all generate pixel data very much differently in unique ways. Even their window width and their height width kind of determine how well this image is presented in front of us. Using HU values is a way that radiologists can compare patients and their conditions or even their past scans. And here, machine learning and statistical interference and deep learning models use HU values to see what they can detect as abnormalities in these images. So there's some caveats, like I said. Older machines will have 16-bit compared to 32-bit, so it's important to look up the manufacturer. And HU values kind of range from 0 to 4,000. The higher resolution gets, the larger that range becomes. So when you write code or use statistics on top of the data, You really want to do that so you can deal with standard deviation. There's going to be so much variance in the data. Each patient is going to cause a different deviation on a sort of bell graph in a sense. All right, so essentially what I explained is the data itself, its data structure, what a DICOM file is and what it contains. And then pre-processing, converting the data into values that are usable by a deep learning model. So for your homework, I want you to watch this YouTube video and then read some documentation on this IP. Whoever generated this documentation here did not put a URL. Stanford started this technology in a tutorial a long time ago, so also read that. You also want to check out the full pre-processing tutorial by Guido Zudoff. So those are my citations. Wikipedia can also explain some of this encoding if you're more hardware minded and into how bits and encoding works a lot of the time. And then this is also just related to a lot of data structures. So thank you. That is the lecture.